Hey everyone, so my name is Anil, and in this video, we're going to learn how a document chat app works and how we can build one quickly, right? So, the basic idea of a document chat is where, as you can see in this demo, which we're going to be building, you can enter, you can upload a document and then you can ask it queries about different parts of the document, right? And the LLM based workflow goes ahead, retrieves the relevant pieces of information and gives you the answers. And this is quite common now, becoming very useful in a lot of fields. A lot of you have probably already done this with ChatGPT. It's also relevant with databases that are your own, like if you're building a legal database or a financial report database or a report of all your company's documents or so on, right? And so this is a classic example of RAG. And over the next few minutes, we're going to see how this works and build one quickly. So how are we building our document chat example, like I just showed you in the demo, right? What you want, as I said, is a document that you can ask questions to. So, the repository we're going to use for this is Laeyerz. You can check it out on GitHub, and we'll get to this when we start coding. It's a small workflow repository we've put together to make it possible to or easy to build workflows and agents, right? So, as the name suggests, in retrieval augmented generation, which is what DocChat is all about, you have two workflows, right? You have to retrieve, you need to first store. So the first step is the storage workflow. And what that has is you have a document. First thing you need to do is, and this, so we're breaking this into nodes in a workflow, right? You need to extract the information from it. So you have a file and you need to get the information. In our case, we're going to use a library called fits to extract information in the form of pages. But there are a number of startups that actually kind of specialize in this, right? Like Reducto and Landing AI and even Google, Amazon, Microsoft all have the APIs. Focus on handling complex documents and extracting the relevant information. Once you have that information, especially if it's a document, you want to break it into pieces because what we're doing here is standard RAG where you're going to use vectors to store the information and then handle it with semantic search, right? Now there are other approaches that have come in as well, like vectorless RAG and graph RAG and so on. We'll cover them in future videos, but in this case, we're going to focus on standard RAG, right? So what you need in our case, we've got the pages out. What you need is to break it into chunks. We're going to use two steps. We're using fits to get it as pages. We're going to write a little simple code where we're going to combine that pages into one piece of text. And then, given that text, you're going to define the size of the chunk. We're going to break it into sentences. And then, depending on the size of the chunk, where you want to say, a group of text is a certain number of words, we're going to break it in that way. So, what you end up getting is this document in pieces like this or chunks. Once you have the chunks, each chunk then becomes a vector. And that is where context is kind of obtained. You use what is called an embedding model. We're going to use the sentence transformers library from Hugging Face that takes these chunks and the model and converts it into a vector. So in this case, it means what type of model, not this is the algorithm, what is the name of the algorithm. And each chunk then becomes a corresponding vector like this. And that is then stored in the vector store, which is a database that can store these vectors. So we're going to use the face library from Facebook because we're creating a temporary store. We don't want to store these documents for posterity. If you're using that, you use something with persistence. So you can add a database to store that information, the vectors in the long run. In this case, it's just in memory, and then when I close the application, it's gone. But you can use vector stores like Chroma or Pinecone or something like that, and it is stored either locally or in the cloud, and you can always retrieve it. So if you're building say, I don't know, legal database or a financial report database, you want to keep accumulating that information, use a document library with persistence. But what that does is takes the vector and the metadata as chunks and stores it in the data in the library in the database. And effectively, what you get is a quick way of referencing that information. So now, when you give it a query vector, it quickly gets the closest vectors, which is called semantic search, meaning it's able to find the passages or chunks with the best context relevant to your query. Now, chunking is one of the most crucial. Extraction and chunking are some of the most crucial pieces of this puzzle. We're using a very elementary approach, but the better that stage is, the better your search is. Now, when you're done with this part of the flow, we're done storing our document. So let's go quickly set this up and we'll come back and look at how you're going to retrieve the document. So this is an example of the document. We'll kind of run through a doc chat system. So I've just taken this out of Wikipedia, but it's a small PDF that contains a little information on AI, right? And so it's got a couple of pages on AI and knowledge representation and machine learning and so on. And the idea is to see if this document, it's got 5 pages. The idea is to see if this document, when we pass it in, we can get specific pieces by chatting with it. Okay, so let's now start coding this up. So to build this workflow or these workflows, you have two workflows here. You need the Laeyerz library, so which is what we build our workflows with. So you go clone it from GitHub, github.com/pexagon/layers, and then once you kind of get that repository, do cd into that repository and just do a pip install -e dot. And we will, at the time of this recording, we will kind of slowly, pretty quickly actually get this up on on pip as well, so you can do a direct install. You also need to install the OpenAI API because that's what we're going to be using, as our LLM. And then kind of to convert that into a workflow node, and we know in Laeyerz, if you've seen previous videos as well, you'll kind of note that we kind of convert everything into nodes, which is a Laeyerz component, and then kind of connect that using edges and so on. So we already have OpenAI set up as a node. Once you install this, go ahead and clone this repository called Laeyerz node. So you can just go get that particular node as well, just download that, which is the OpenAI node, right? And so that is the wrapper here that converts it into a node. So we won't set up that specifically here. We'll convert everything else into a node here, right? So go get that as well. And then we need a few libraries. We need Fez, which is going to be a vector store. We need sentence transformer, and then fits, right? Which is where, which is how our PDF is going to be extracted. From Laeyerz, we need flow and node. This is our workflow. This is how we build custom nodes, right? We get key manager, which manages our API keys. We need that for OpenAI. Prompt node actually is optional in this particular case. It helps to build the prompt, but we're going to build that explicitly here. And then, of course, we get from Laeyerz nodes, OpenAI node, right? Which is a wrapper around that converts it into a node already. And then, of course, we need to get our API keys. In this case, there's only one because our vector store is local, right? So we are not going to need a key for that. We just need the API key for OpenAI. So you can use the key manager in Laeyerz if you point it to an API key file. In this case, I've stored it in an env.json, but it could be a .env as well. Point it to that and it will get the API keys from there. Okay, so now that we've got that, let's get started writing our nodes, right? So the first thing we need to do in this workflow is extract the document, right? So we give it a file and we get out the document. So we're going to use fits, right? Which is a library available, which is pretty easy to use. And then set up a fairly elementary document extractor, right? Now this is fairly straightforward and elementary, meaning it works. But if you want to use complex documents, complex annual reports, and so on, recommended that you can switch this with something, either customize this or switch this with something more powerful. You could use something like Reducto or Landing AI or Google's API or something, and you can get things like tables and figures kind of extracted better. But this suffices for most simple documents, right? So how we set that up as a Laeyerz node, meaning as a node in the workflow, is I create a function called PDF loader, and in that I just make sure it inherits from node, which we have imported here, right? The rest of it is fairly straightforward. So when you set up the init, take in a node name, which is something the parent node requires, and then a config, right, which can be empty. For our LLM case, that's where the API key and the model name and all go in. And then we call the parent class, and then that's that. And I'll come back to this, but the function here that we have is load PDF, which takes in the file name. And then what we do is we go ahead and with fits, we open the file name. And then this is a little bit of kind of code to get the different blocks. So in fits, you can extract text as blocks. And then we do a little bit of sorting. You don't need to worry about the logic here. The basic idea is you sort, so if in our case, we're using a simple example, but in case the file is more complex, has complex layouts, it allows you to sort the block in a fairly elementary way. Now, this works for certain kinds of simple kind of layouts where it's kind of, sequential, and then converts that into pages. So it gets it page by page. And what we extract are the pages, right? So it basically says page with a number and the content, which is what we need. And it returns a dictionary. And with Laeyerz nodes, I recommend you return dictionaries. You return other data types. The wrapper is able to handle it, but ideally, if you're writing your own functions or classes, if you're not wrapping around something that exists, then just return it as a dictionary. So I return doc pages. And once you do that, to convert it as a node, we've added this add actions function. Now the parent class node has an add action function, which gets called from here, and an action basically in a node in Laeyerz, an action is basically the function that gets run, right? And it allows us, so if you have just one function, actually you don't need to make it a class, just say def function. And we've seen that in previous videos where you then just go and define the node and use the add function method, right? But here what we do is we're defining it as a class. So what we do here is you set up the inputs to that function, which in this case is a file name, and then the outputs, which is the doc pages. Give it the name of that variable and the type, and then description works only if you're using this as a tool for an agent. So you don't need to worry about that now. And then because you've inherited from node, it has an add action method, right? And so you say self.add action, give it the name, which is load PDF. Ideally this name same as the function, but can be anything. Give it the function, give it the inputs and the outputs. The rest of the things is default and stuff. You don't need to do that. So till here, you can do that. And what ends up happening is this node now becomes a workflow node. And the actions are the functions that can be called. What that allows us to do is have and you'll see that later with the vector store, where you can have a class with multiple actions. And in the workflow, you can decide which one you want to connect to. So it's kind of a, instead of having each action separately, and then maybe like, for example, in FAIRS, you have a state that's common to both. You can have multiple functions in the class, and then the member functions can be made effectively workflow nodes, but we're calling them actions using this self.add action. So we've done that, and that sets up our text extractor. So that allows us to take in a file and convert it into pages. What's the next piece of the puzzle? The next piece of the puzzle, so we can just initialize this here as well. And that's that. The next piece of the puzzle is we've got these pages, right, from the document. You want to break them into chunks. So let's do that. We've broken each step into a different node. The advantage being you can kind of monitor each piece of the workflow. So you can use something else to extract, you can use something else to chunk, or you can use one node to do both of them. But either way, breaking it down means our workflow is fairly flexible, and extending it in the future is much easier, right? So the next thing we need to do is convert that into chunks, right? And so I'm going to actually make a small change here. I'm going to say text processor is chunk. So again, I'm creating a custom class inheriting from node, and this is the same. You pass in the node name. The name allows you to kind of tag it, right? And that is again going to be useful. We'll see. So I call this PDF loader. This name is what we're going to use when we define the edges. So I've got two functions here. One is to combine because we're taking in pages from here, right? So you have two steps. First is to combine the pages. So all it does is takes the pages and combines them into one big piece of text. Now this is just the way I'm doing it. It's a simple text extractor. Ideally, there are more complex ways to do it. LangChain has a recursive chunker, that is a good one. And then of course we're using tools like, I don't know, Reducto, for example. You get well-defined JSON chunks and you can extract the pieces from that, right? And we'll do that at a different point where we look at different ways of chunking and embedding. That's a different video, right? So you have two functions, one that takes in the pages, converts it into text, and the second that then breaks the text into chunks. And how it does that here, it's not a very smart way, it's a very elementary way. It assumes that a sentence is, where the end is with a full stop. So it breaks it or splits it by the full stop, then combines the sentences till the size of the chunk is greater than 200 words, right? Because it's splitting by space. So if you have more than 200 words, then that is the last sentence in that chunk, but the sentence is fully there. And then it starts the next chunk, right? And that's kind of what it does. You have a padding parameter here that you can pass in. I'm not using it here in this case. What padding does is allows overlap, and it's recommended, but this is a very simple, example where the padding is not there. Ideally, if you have padding, you then go back one sentence and do the overlap, right? But at the moment, I'm not doing that here. But I've left the option open, and when we explain chunkers, or when you look at this code on Git, you'll probably see more updates, right? Where I'll kind of add more complex chunking strategies. So in this case, you have two actions, right? Basically two functions that can be called by the workflow. One is combine pages, and we're separating this because I think that's a better way to build a workflow. Also helps with agentic workflows in the future, where you have different functions and the LLM can decide which one to call. It might not want to call this. It has just one page. It calls the chunking directly and so on. So what we do here is it inputs to the first function. Combine pages is just the pages which we've got from Fitz, and then what it returns is just the text, which is the pages combined. We've defined the inputs here, and then you call the add action with the name, the function, the inputs, and the outputs. And then the second action is the split text action, right? Which is going to take that and actually create the chunks. So it takes in the text and it returns the chunks. So string and list. And again, we call the add action, which says split text, function is split text, and split text rather, and then inputs and outputs. And that's that. We've got the chunking part solved. So let's just go quickly run this, and then what I'm going to do is create the node of that, and we're just creating it right there. And so we are sorted with the chunking. Now the third node is the embedding model. So as you've guessed from the imports, we're using sentence transformers. And so that's a fairly easy to use kind of model that I've got from Hugging Face. So that's where the import is. We've got from sentence transformers, and that is a library you get from Hugging Face. And then got a default model name, but you can specify one if you want. So again, we've created a small wrapper around that. All these are available in the Laeyerz nodes repo that I've shown above. So apart from the LLM, you can see that as well, and you can go ahead and get them. You don't have to rewrite them if you don't want. But same approach, right? We've used that, and the model here we have an internal state. So in these we don't have an internal state, right? But here we do have an internal state, which is just the transformer model. And then you have the encode function, and that's it, right? So if you say model.encode sentences, which is a list of sentences that are passed in, which is what you get from the chunker, it returns them as embeddings, which is vectors handling the text. So we do that and use the add actions function. And so we set up this action by saying we takes in sentences, which are the inputs, and returns embeddings. So the action name is encode, function is self.encode, parameters we don't worry about, and we have inputs and outputs. And so we have a third node with one action, one function, which is the encode function. And that uses the sentence transformer encode. So that's our embedding model. Again, pretty straightforward, pretty quick to set up actually when you do DocChat. So next we have to set up our vector store. And like you've seen above, use the face library from Facebook, which is a quick way to set up a local vector store. So in this case, our DocChat is not storing the document in a long-term memory store, right? It's storing it temporarily. We ask it the questions and then it goes, right? Now, if you want to retain the storage, then you either have to add to this, a database that stores these vectors and chunks for after your session is closed, right? And you can do that either by specifically adding a database or use something like Chroma, right? Or if you want to put it on the cloud, again, Chroma, or use Pinecone or something like that. And it persists. So if you're building an application where you want the data to accumulate, you have, I don't know, building a legal database or building a repository of annual reports for financial analysis and so on. You want to keep adding that information. So use a persistent or a cloud-based vector store. In this case, the idea is you upload your document, I chat with it, the document's gone. I'm not interested in it anymore. And so this is perfect for that. So, and you don't need this because it's a node. So what we do is we set up the face node and you have node name and config, right? Which is the typical inputs to a node. And then what we do is from config, we need to pass the vector dimensions. So that's the one input this needs, because when you create an index, and if you look at the detailed video we've done on vector stores, you have to create an index, right? Which is what vector stores do. They take your vectors and then store them in an efficient way, create an index, which then can be queried very quickly, as we'll see here, to get the vectors quickly. I'm using the index flat L2, which for smallish databases, I think they say less than 100,000 is perfect. And so it does an exhaustive, Euclidean L2 search, right? It looks for the L2 norm difference between the vectors, and it works for small examples. For larger examples, you have to do an approximate search, right? But on Face's documentation, they have recommended that this works for small examples. So I'm using that. So it takes the vector dimension, and then actually you don't need this. You can just directly call the index face.index flat L2 self.vector_dim and creates the index. You can optionally store the metadata. I'm not doing it in this. Well, I am doing it here, so that's fine. And then that's that. And now you have two functions or two actions, right? You have the store and the search. So in the store, you're passing it the vectors and the metadata. And what does it do? It stores the vectors, right? And it also stores the corresponding metadata. And then in terms of search, what do? You go and you tell it how many search results you want. So in this case, if case 3 is the default, the closest 3 results, right? And then you go in and pass in the query vector, which we'll see when we do the retrieval part of the pipeline. You get the indices and the distances. So you get the 3 closest vectors. And then once you have the indices, meaning you know which ones it is, you go and extract that corresponding metadata from here, from the self.metadata, and you return that, right? That's that. So again, very simple. Again, these are not meant to be complex, meant to demonstrate how you can quickly build DocChat. And then, as we get more advanced in further videos, we'll as we explore some of these chunks in more detail, or rather some of these pieces in more detail, we can add more complex vector storage or much better chunking algorithms for sure. All right. So in this case, two actions. One is, the store inputs, right? And you don't have an output here. So you want to store, and the inputs are the vectors and the metadata, and there's no output. It's just going into the vector store, and that's it. You don't need a step after that, right? For the workflow. So add action, self.add action, the name is store, the function is store, and the inputs and the outputs. And the other is search, which is in the retrieval pipeline. So we're actually focusing on the storage pipeline or the pieces for that. But, when you define the node, you define the whole thing. So query vector and the number of results to return. And the outputs for that are the results, which is the structure we're setting up here, which has the metadata and the scope. So that is that. And you set up that action as well. And that is your vector store setup. So let me just set that up as well. And we're done. We have one missing piece of the puzzle, which is create a vector dim. And that's because I've not added the config here, right? So let me just add the config. I say vector dim. And 384 is the size dimension. So let's do that and you're done. So the config is essential here because the store needs to know the size of each vector, right? Or the length of each vector. So we've got the pieces we needed to create the storage workflow. And for retrieval, actually, again, you only need one more piece, which is the LLM, which we're importing. So actually, our basic node definition is done. So the next step is to go ahead and create the storage and the retrieval workflows. Okay, so now that we've created the nodes, we need to create the workflow. And we have two workflows here. We have the storage and the retrieval workflow. So to create a workflow, we've already imported the flow class from the Laeyerz library. Create the object, store flow is flow, and give it a name. And then what we need to do is add the nodes. So for example, we have created a PDF importer above called PDF loader, right? And we've instantiated it here. We've got PDF loader this. Well, this is a node, right? So we say store flow.add node, PDF loader, right? And that loads the PDF. That adds the node to the workflow. Doesn't load the PDF yet. Similarly, we have a few other nodes. We have the text processing, and I've instantiated it here as combined text, I think. Yeah. So or combined pages to combined text. So I'm gonna add that node. There's the embedding model and the vector store. And those are the nodes. So this adds the nodes to the workflow. Now, once you add these, what the workflow looks for are not these names, right? So we'll see that as we define the edges and the data connections, what the workflow looks for is the name you add when you instantiate this node. So for PDF loader, it's this. And then because nodes can have multiple functions, you also have to point out the function, right? So in this case, if you want to call this function, you have to say PDF loader load PDF. For chunk, for this one, so text chunking, well, we've called it combined pages. I've used combined text here. It's combined pages. We're going to say combined pages and then tell it whether it's combined pages function or split text function, right? For the vector store, we've defined it as vector store or document store. And then what you have to tell it is whether you want store or search, right? So when we define the edges, which is next, so once you're adding the nodes, you don't need to specify all of that. But now edges, which is the flow of control in this workflow, meaning it tells the orchestrator where to start and then which function to call, right? It doesn't control the flow of data. That is next. We'll define that next. It controls how the orchestrator executes the functions or in which order. So how do you do that? You say, well, store flow dot add edge, and you say start, and then give it the name of the node, which I just showed you above, and the action. So you go to PDF loader, which is the node, and call the load PDF function. What's the next piece of the puzzle? Well, this should get the information out of the PDF in the form of pages, right? We've seen that above. What you want to do next now is go ahead and combine that into one piece of text, right? So combine pages. Now, if we had defined the chunker as one function, you just have to call that. But in this case, we've defined it as two pieces, right? Again, the idea being to make it more flexible and to show you how you can use nodes. So combine pages, right? That's the name of the node, and this is the function we're calling. And you'll see again how multi-action functions become useful, because now after this, the next function you want to execute, or the next action, as I call it, is split text. You have got the text from the PDF, you have combined it into one piece of text. Now you want to chunk it. So we go to combine pages, split text. Once you do that, what do you have? You have the chunks, right? The split text gets you the chunks. So well, what do you do next? Call the embedding model. So this tells it from here, go here. So the format now you can start seeing makes sense. You want to go from start node, start action, to next node, next action, right? Yeah, let's just call it. That's the format. So this node, which is the previous node, to this when it gets here, it now goes and looks for this edge, says, oh, okay, where am I supposed to go next? I'm not supposed to go to the embedding model. Now, when you have branching and stuff, you end up with conditional nodes. That's something that we're working on, and that is for a different video, right? But in this case, actually the flow is pretty linear, so you don't need complex conditional nodes. Once you have the embedding model, so when you set up this edge, combine pages to embeddings code, it does go to the embeddings encode, right? Meaning the control now is here. Last piece of this puzzle is to store the vectors. You've got the chunks here, you've got the vectors here. Now what do? You go to embeddings encode and you store the vectors. And technically the flow is done, but kind of follow format and tell it it's done. You define end. So if you say documents, when it is done with document store, it goes and says, what's the next edge? It sees end and it says, okay, I'm done. And that's the way you define the edges in the workflow. Is that it? That's not it, right? We need to define how the data flows. We've seen that these functions have different inputs, and we need to tell it where to get these inputs from, right? They're stored in the app state or the graph state, depending on what you want to call it. Each of these are executed and the inputs come in and they're stored, the outputs are stored in a graph state. And that's why you define the inputs and the outputs. The outputs you defined in the node above. So in this case, for example, you said outputs results. This is posted in the graph state, right? The graph state has an entry for this node. So it has an entry called document store, and then it'll have an entry for this action. So search, and the output results will be stored there. How does whichever node know to call that, right? So data sources or data connections have to be defined. How do we do that? So we do that using the add data source method in Laeyerz. Again, if you look at some of our previous videos where we define simpler workflows, you can see how this works a little better. It's less complex, but hopefully this is becoming clear to you. So if you're extracting something from the inputs is what goes into the workflow, right? In this, I say flow.run, this is the inputs. If you want to extract something from there, just say inputs and give it the name of the variable. All we give it is the file name in this case. And where is it going? It's going to PDF loader, load. So the load PDF file name. Now the convention is slightly different to the add edge, in that in this case you're telling it where I am and where I want to go. In this case, I'm saying what is the socket or what is my variable and where do I get that value from. So in this case, the convention is socket node, socket name, or rather socket function or action, and then socket name. So, or rather, instead of socket, I can also call it source. And then what you define on the other end is where it's coming from, right? So actually, this is not, this is target. And then you have the source. And if it's a node action, and then the name, right? The variable. So in this case, PDF loader load PDF has one input called file name, as we've seen above, and that comes from the inputs to the workflow. Inputs is inputs to the workflow. What other data connections or data sources do we need to add? Well, what about combine pages? That's the next function. What does it do? It takes the output of the PDF loader, which is doc pages. We've defined this above. So just a quick check here. The output is doc pages. We can see that here. And the input to text processor is pages, right? Pages. So what do? We say combine pages. The action is combine pages and the name of the variable is pages, and it gets that value from the PDF loader load PDF function doc pages. Next, we need to split this. So where does the split text get its information? The output of this, right? So combine pages text is the output. These are all names that you have defined above. And split text. So this is and so in this case, it isn't split text because we've only used one node. It's called combine pages. In an example, had used them as two separate nodes. So combine pages, we call the function split text, and the variable we need is text. What's the output of this? So the output of this is chunks. And where does that go? That goes into the embedding model. So the embedding model, so just take each of your nodes and look at the inputs for each function and then find out where it comes from. So in this case, the embedding model takes in sentences. That's the variable name I've used here, right? I should have used a better variable name, but I've used sentences. So that's fine. And, that's the input variable name used here. It should be chunks, but, and where does it get that? It gets that from combine pages, split text function. And the output of that is chunks, right? Which we're seeing here. Chunks, right? For this text processor node, the action is split text and it returns chunks. Once we've got the embeddings, you go to the document store and you want to store, and that function takes in vectors, which is basically the embedding model's output. So the embedding model encode embeddings. And then what it also takes in is the metadata, right? It takes in the actual text associated with those chunks. So it's got the vectors, but also needs the text. And that is from the text splitter, which we're calling combined pages. So it's going to go into combined pages, the split text function, and it's got the chunks here. It also takes that in, right? The embedding model also takes that in. That's where it gets the vectors and the metadata. So these are the edges for your storage workflow. And that's it. We have defined our workflow very clearly. And so now what are we going to do? We're going to give it the file, which we've just seen when we started this video. We saw, an example of a file. And, it was a very simple snippet from Wikipedia, which on AI, right? So we're going to load that file by saying, well, this is the file name, and I've added it in the same folder. So it doesn't need any more path or anything else. And I'm going to say stored flow.run file name. And as you can see, it goes in, it runs the PDF loader, combined pages, and so on, and it stores it in the document store. And so what we have done is now stored the chunks from this file in the document store. Now, if you want to visualize some of these pieces, what you can do is say store flow dot graph state, an object, and then you want to get the values associated with this. So I think it is state, and you have associated with each of the inputs as file name. The PDF loader actually has these pages, as we can see. And then the embedding model has a list of embeddings and so on, right? So we get to see now search, for example, hasn't been initiated because it is in the other workflow. But you can see how the graph state actually stores the embeddings and so on. You can't see the vector store part because the vector store is actually storing it. These are parts of the graph state. The vector store is actually storing it inside the node, right? So it's actually stored here. And so it is actually a stateful node. Ideally in workflows, you use stateless nodes, but it's actually stored here, right? And so that you can't see. We'll see that when we retrieve, right? We're able to retrieve it correctly. So that's the storage part of the workflow. The next piece of the puzzle is the retrieval part of the workflow. So now that we know how to store our document, we need to figure out how to retrieve it. Now the retrieval flow is where you have a user giving it a query. First step is you want to do semantic search to get the relevant chunks. So what we want to do is use the same embedding model we've used to store to take this query and convert it into a vector. Once we've done that, we pass that to the vector store, but now instead of storing, we're searching or querying it. So we tell it this is our input vector, which is what the query was, and telling it the closest number of results we want. Don't always get 1, get 2 or 3, right? So get, say, 3 of the closest chunks. And those are the chunks that semantically are the closest, meaning they're the closest. How does that work? Well, the embedding models that we use are trained to try and convert it into vectors that are semantically relevant. So when you use the same embedding model, you get pieces of the puzzle that are relevant. Now, ideally in retrieval as well, depending on the storage, if you've added a knowledge graph, if you've added keyword search and so on, use all those as well, because the better your retrieval, the better the chunking and better the retrieval, the more context you're giving to the LLM, and the more context you give to the LLM, or the better context you give to the LLM, the better the response. So the prompt, which is what goes into the LLM, basically has instructions telling the LLM that it needs to take this information or context I'm giving it and answer my query based on that. It's got the chunks, which is the information got from the vector store. Now, if you're using more complex methods, you would add whatever context associated with that there and the initial user query. And the LLM takes that. So it's returning messages here. It's taking those messages. And the model you're calling, in this case, I'm calling OpenAI, and I'm using one of those GPT series models. And you can use GPT-5 mini, which is good in most cases. You can also use GPT-5, which is also even more powerful. But I think I'm using GPT-5 mini, and then you get your response. And so that is basically the retrieval part of RAG, and that's how document chat works, right? You have the storage and the retrieval flows. So let's go quickly build this and then look at our demo. Okay, so to do the retrieval part of the workflow, what do we need? We have the input coming in. We need to embed it. So we have the embedding model. Now the embedding model, we already have the embedding model above. I'm just going to define a separate instance of that. Same embedding model, we've created this node above, but I'm creating a separate instance of that. So that will take the input text and convert it into a vector. The vector store is the same as above. We don't need to create a node. What do we need to do next? We need to convert that into a prompt for the LLM. So we're going to create a custom prompt node. The function that takes in the instructions, the context, and the query. Then what does it do? The context, the assumption is it's in chunks, and the vector store gives us, if you look at the vector store above, when you do search, what do you get? You get metadata and score. We just want the metadata part, right? So I'm going to process that in a custom prompt builder where it's going to go in and get the text by going through each chunk that is returned. So if we say vector store and I want two chunks, the two closest vectors, it will get those two chunks. I'm going to take the data from that and just attach that. So that is context text. And then the messages to the LLM, I'm using the messages API, is instructions, context text, and the query. Okay. So converting this function into a node, this we have seen in previous videos where you just define the node. We have not made it a class. It's just a function. You define the node. I'm going to call it prompt node. Define the inputs. Define the output. And then just say set function. The name in this case. So we know the name of the node is prompt and the name of the action or the function is prompt as well. Give it the function, which is this, and inputs and outputs. And that creates a prompt node for us, right? And in this case, we don't need to create another instance of this. This is just the node, right? So that is that. In that case, it was a class, just to differentiate. So you're creating a class, you have to instantiate it. In this case, you're directly creating a node. And so when you do this, you've already instantiated it, right? And so because you're creating basically an instance of the base class node and adding a function to it, which works if you have one function. If you have more, then recommended you make it a class, because, well, if you have internal state variables like we had vector or we have the index or so on, you can store them in the class and all that information is together. Okay, so we've got the prompt node. What we need next is the LLM, right? Once we get the prompt, we need the LLM. So from the key manager, which we've imported from Laeyerz, I get the OpenAI API key, which is how I've defined the API key. This LLM node, we've seen 3-4 instances of how we've created nodes. I've just created a wrapper for the OpenAI LLM. So you can go get that from, as we've done above, the Laeyerz nodes repo on Git. And what it takes in the name, I'm just calling it LLM. And the config is the API key and the model. And you could give it instructions, but in this case, I've handled the instructions in the prompt itself. So I do that, and our LLM is set, except that key manager is something I haven't defined above. So let's just go above and check that out. And I haven't instantiated key manager. Let's run that. I come back here and that is that. And these are the nodes we need for the retrieval flow. The retrieval flow is actually fairly trivial. So we've got that. Actually, let me just, this is about, that's that. And embedding model we've already defined. So now let's create the workflow for that. So it's the second workflow. I'm going to call it the chat And so I'm going to call that doc chat. I need to add the nodes. It's pretty similar to what we've seen above for the storage flow. In this case, I have to add the embedding model, and it's embedding model 2 because that's what I've defined here. You can use the one above as well, but it can sometimes, in some cases, lead to conflicts, right? Because of edge confusion. So create a new instance. So using the same action, create a separate instance. You're using a different action, it doesn't matter. But in this case, it's just got one action embed, right? So, or one function that it needs to call. So embedding model, the vector store is the same. The reason being that I need that state. I've used store there, I'm using retrieve here. But the vector store is actually stored in that class object, right? Because it's a local vector store. If you were using something like Pinecone, for example, it's stored in the cloud. You don't need to create this again, just use a different, use the API call. But in this case, the state or the vectors are stored in that object. You need the prompt node, which we've created above, and the LLM. So those are the thing. I haven't defined this. So we need the edges now to define the flow of data. Now, flow of control rather. So start to embedding model encode function to document store search, right? Then document store is this vector store, right? We've named it document store as you've seen above. From search, once you've got the outputs from that, go to prompt, which is the prompt node. As we've seen above, we've called it prompt and prompt, capital here, small here. And from that to the LLM. And for the OpenAI node, the action is call LLS, right? So I'm going to define that and you're done. Getting confused with embeddings because I think I've named it differently. I've called it embeddings 2. So that's my mistake. And I redone that, and that's that. Okay. And then add your data connections or data inputs. So I'm going to say so I'll explain this in a second. What we have to do is when we add the data connections, first the embedding model, right? So the input passed in is the user query. First thing you need is the embedding model. So let's go there. So the embeddings 2. Let's not forget that. Encode function takes in the sentences, which is the input query, right? We're passing an input. This is the example. You're passing the user query, and that goes into the embedding model. Then what's the next thing that is run? We need the vector store search. So document store search. You need two things. You need the query vector, which is obtained from the embedding model. So embeddings 2 encode embeddings, which is the output. The inputs are the sentences, the output is the embeddings. Second, you need K, which is the number of results to be returned. If it's not, connected to some other part of the app state, you use set node input. Instead of add data source, you use set node input. So document store search values 2. So that sets that value to 2. Then the LLM, or the prompt rather. The prompt takes this information, converts it into a prompt. So it has instructions. So I'm defining the instructions above. You're a smart assistant, answer the question, and so on. If the information is not in the context, you need to say it's not in the context, right? Don't speculate. So again, use set node input to define the instructions. You could pass this in as a parameter to config as well, but for now this is good. The context is obtained from the document store. So document store search results. And then the query is from input. So inputs query. And then of course the LLM. So I'm going to say tools. There are no tools. It's not an agent or in agentic mode. And then the messages is from the prompt. So prompt, and I've used the variable prompt as well. I should have used messages, I guess, here as the output. But for now, let's just keep it as it is. And that goes to the LLM, call LLM. And the input to that is messages. You can go check out that function. You'll see that the input to that is messages. So that sets up our data connections. And I haven't set up LLM instructions, so my bad. And that's that. We've defined that workflow. Now, in this case, we do, unlike the store workflow, we want a value to be returned, which is the final response of the LLM. So in this case, you set the output of the workflow, because otherwise you have to go search like we did above the graph state to get out the value. So what you do is say chat flow, set outputs, and give it the name of the value. In this case, we want the LLM's output. So LLM, call LLM, and the output is labeled content. So LLM column content. If you want to, for example, extract an information from, say, the doc store, so search results, well, add here this value, right? And what it'll do is in the outputs, which is a dictionary, it'll have this tag and the value of that, and this tag and the value of that. So it's basically extracting those values from the app state or the graph state, which is where it's stored. So I set the outputs and we're done. And that is how it works, like how it's set up. So let's test it out. What do? We go and say the query. What is the main topic of the document? Now, I've shown you the document before we started building this. It's a document on a Wikipedia document on basics of AI. So I just say, okay, user query, and how you pass it into a workflow like we did above, dot run, and the variable name is query, and you give the user query. So it takes in an input as a dictionary, and then outputs is what it has. And because we have set outputs in the if you see above in the storage flow, we didn't set outputs because there is no output, because it's just storing it into the vector store and it's done, right? We don't need to see anything. In this case, we want to see the output, so we've defined the outputs and say chatflow.run query user query, and then the output is a dictionary as well, so key value in output.items, and then you get the value, right? So let's go run this, and it runs the workflow, it embeds, does a document search. You see the two closest indices. So you see 2 and 4 are the two closest. And then it's gone and got the scores for that. And now if I visualize the output, it says the main topic of knowledge is artificial intelligence, right? So let's do something now, which is a little fun. Let's go. I've taken this workflow now, made a small modification to it so that it can be connected to a backend using Fast API, and I've converted that into a chat app, right? And we have a simple HTML frontend as well. So in the Laeyerz examples repository, I'll add a link to that, different Laeyerz repositories, but all the examples are the nodes are in Laeyerz nodes. The examples, all these tutorials we do are, or examples we do are in Laeyerz examples. So if you go there, there's a small HTML frontend. Let's take the same document and let's ask it a few questions. This has been connected to a Fast API, so you can upload a document with store and chat. So let's go take a look at that. Okay, so let's go ahead and test this out, right? Like I mentioned, I'll show you the GitHub repository in a second, but we've created an HTML file and we've converted this, taken these workflows that we've just seen, but now use the Fast API to set up a backend that will call these flows. Not designed to be very scalable or anything like that. It's just a simple example. So it'll work as I'm showing you, and then you can go ahead and modify that if you want it to work in production. I've chosen the file, I've hit upload. And so it uploads it and it returns the text. So we're seeing artificial intelligence refers to and so on. It's just returning the pages, right? It's founded and so on. And let's enter a question. So what is the document? Takes a second because it has to run through the workflow. And then it gives views about artificial intelligence. It covers all of this. Okay. So what is, right? Which is, again, it should look at this document. And then let's ask something else. So it takes a second to think, but right. And it's extracting from this, right? It's extracting from this, it's extracting applications, and so on, right? And so let's ask it something slightly more tricky. It's called so Markov decision process. Okay, so can you tell me about a Markov this? Now, what you'll see here also is in some examples, because the chunking isn't great, it isn't able to figure it out, right? And so if it isn't able to figure it out, it does, in this case, it does a good job. It says a Markov distribution transition model describes them. So you're seeing it's getting this chunk, right? So we're seeing some examples where it's working really well. I'll show you an example where it doesn't work very well, right? Okay, so it has a reference here to ChatGPT somewhere, right? So can you tell me about ChatGPT and such? And it is actually, funnily enough, asking OpenAI, but it says, sorry, the information is not provided, meaning it's not able to detect this chunk. So some of the issues also I wanted to show you that it does really well in these, because when it's able to get the chunk, but it's not guaranteed to get the chunk. It hasn't been able to get this chunk about ChatGPT and say, actually, there's a reference here. So it just has to say it's an application of AI, right? But it doesn't. And so that is where adding more complex chunking strategies, adding semantic search and so on. Well, we have semantic search, adding normal search, keyword search, and so on, adding knowledge graphs will improve this significantly. And that's what you see in complex production systems, even a chat GPT, for example. But you see that it works, it does a decent job, right? Given conditions we've used and the embedding model we've used. Okay, so hopefully you've enjoyed this video. Hopefully it's given you an understanding of how this works, how DocChat works and how you can build one quickly. I'll just show you the GitHub repository in a second as well if you're interested. So you can go ahead and check out where we have this code and you can go ahead and run it yourself and hopefully modify it, right? Okay. So to see where you can get this example code, you go to Laeyerz examples, the Laeyerz examples repository on GitHub, and it's with Pixagon Laeyerz examples, and you go to DocChat. There are a few different examples, and you have just the flow is in DocChat flow, but you have DocChat app, which what it does is takes the workflow we've built, so right, but actually what it does is sets it up here again, and then uses fast API to create a few routes, right? So store, chat, and so on. And that then allows us to then talk to it or make it an app that then with docchat.html, which is a simple HTML file, it creates the interface for that. So this is kind of where the code is. You can go ahead and I'd recommend you, if you have the time, play around with this. So hopefully this kind of video has given you an understanding of how document chat works and how you can build one quickly. And hopefully it's given you a bit of an understanding of how you can use the Laeyerz repository to build one as well. So hopefully you have enjoyed this video. Stay tuned for the next one. So hopefully this kind of video has given you an understanding of how document